Hello everybody, Mr. Hasty here. Today we're going to be talking about section 11.2, which is on the electromagnetic spectrum. So, yesterday we talked about what the electromagnetic spectrum is. So, quick recap. The electromagnetic spectrum is a set of waves that are non-mechanical, meaning they don't need a medium. They can travel through empty space. They can travel through mediums, they can travel through air and water, but they don't need a medium in order to travel. They're called electromagnetic waves because they're built by alternating electric and magnetic waves that are always together. They always go together. You never have an electric wave without a magnetic wave and vice versa. So all the different electromagnetic waves are based on the different wavelengths and frequencies. So we had an equation a while back that the speed of a wave is equal to the frequency times the wavelength. Frequency times wavelength. And we have this lambda for wavelength. So the tricky thing about electromagnetic waves is they all move at the speed of light. So this velocity can never change. Meaning that if the frequency of the wave changes, the wavelength has to change down. So if we look here on the far end of the spectrum, we have radio waves, and they have 10 to the third meters. So that's 1,000 meters. So that's really, really large. The frequency of those waves are somewhere around the 1,600,000 hertz range. So because the velocity is fixed, if one of these goes up, the other one has to come down. On the other end, we have gamma rays, and that's 10 to the negative 13th meters for a wavelength. So that'd be 0.12001 meters. That's incredibly, incredibly tiny. It means their frequencies are actually relatively low to compensate. So that's the relationship between the frequency and the wavelength. And so you can define what a radio wave is either by talking about its wavelengths or by talking about its frequencies. So we're going to look at this. The first section, the kind of longer waves that we have are radio waves. Then we go to microwaves, which is literally the microwaves that are used in your microwave oven at home to cook your food. We'll talk about that. Then I want to point out we have the visible light spectrum. And it has red at this end and violet at this end. And at some point in your life, you probably learned the Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. That's the order they go in, Roy G. Biv, in the visible light spectrum. Well, the area in front of red is called infrared, in front of red. And the area after, past violet, is called ultraviolet. Then we have our X-rays. And then we have, and these are literally the X-rays we use to get images of your bones. Then we have gamma rays. And unlike the Marvel Comics, they do not turn you into the Hulk, but they are rather dangerous. So what we're going to do is we're going to talk about all these different types of waves, what their characteristics are, and what we use them for. So we're going to start with radio waves. Radio waves are any EM waves that are longer than 10 centimeters. All of these different types of waves are going to be defined by their sizes. So they have some of the longer wavelengths. Which means that they have low frequencies. So that'll be something we talk about in each one. Longer wavelengths, low frequencies. And because of that, their photons have very little energy. So these are low energy waves. They're kind of the less harmful, like kind of more moderate waves of the electromagnetic spectrum. Now, we have a lot of uses for radio waves. We use them for audio transmission, both stuff like CB radios and the radio stations you listen to. In fact, the radio station you listen to, a radio station is given a certain bandwidth of frequency that they're allowed to transmit at. So that's how you tune your radio to a particular frequency, and they transmit their radio waves at that frequency, and that's actually how they decide or how it works out that you can tune into the station you want while ignoring the others. Other applications of this include radar. They use radio waves to bounce a signal off of something, and when that signal comes back, they can tell the relative position. This can be used to tell velocities, such as radar guns they use in sports to tell how fast a baseball pitcher or softball pitcher threw the ball, as well as radar they use to detect planes and things in the military. Magnetic resonance imaging, MRI machines, use radio waves. They bombard a body with radio waves, and then the reflection of those radio waves back allows us to see images of what's going on inside the body. So those are all different uses of radio waves. So microwaves are EM waves between, and these get really small, 0.1 millimeter and around 30 centimeters. Now you might be like, I thought that the 10 centimeter mark, well, there is an area where they kind of overlap, because these are artificial distinctions. We just kind of carved up the EM spectrum into these different categories. So EM waves 0.1 meters and to 30 centimeters, so somewhere in there. So basically, these waves had their wavelength go down, right? So their wavelength went down, which means that their frequency has to go up to compensate. So they're not high frequency waves, but compared to radio waves, which are on one end, their wavelength went down, so their frequency has to go up. Now, the most common discussion of microwaves has to do with microwave oven. So, but we have other uses. We use these for communication technologies. We use these to explore space. We look for background microwave information in space to kind of dictate what has happened. We can use that to make predictions and find out things about our universe. But our most common experience is with the microwave oven. So what microwave ovens do is when you turn your oven on, it's a box, and inside that box is some shielding that stops the microwaves from getting out. And when you put something in there, the microwave oven hits it with a lot of microwaves of the particular wavelength and frequency. And what those do actually is they vibrate water molecules. They're looking for water, H2O, and they vibrate those water molecules. And why is that a big deal? Well, if you remember, what is temperature? Temperature is the average kinetic energy inside a substance. So if you're vibrating molecules and moving them around, you're increasing kinetic energy, which means you're increasing temperature. All right, so now we're going to move on to infrared. These mean kind of like in front of red. And they have very, very small wavelengths. So we're talking 1,000th of a meter. So EM waves between 1,000th and 700 billionths. So we're talking fractions like this. That's 1, 2, 1 billion, million, thousand, yeah. So we're talking fractions like that, meters in wavelength. So again, our wavelength goes down, which means our frequency is going up. So the main uses for infrared technology that we use is we do use it for some communication devices, particularly things like remote controls. Because they transmit a very controlled amount of waves that it's hard to pick up other ways, and so it's a convenient way for us to do short range controlling devices is infrared. Now, the other major use of this is things that have heat. The higher the heat, the higher the infrared radiation. So we use this to see heat. So it can be used as a form of night vision, so that basically you turn on an infrared lens and it will show you hot spots and cold spots. It can also be used to determine how energy efficient a house is by looking at where the heat is escaping the house. So for instance, a lot of houses, if you look at them through an infrared lens, you'll see that the windows or the garage are very, very hot, emitting a lot of radiation, which means you're losing a lot of heat through those areas. So visible light. Visible light is between, it's EM between 700 billionths. I'm not going to write out the fraction. 700 billionths and 400 billionths of a meter. So again, compared to the last category, our wavelengths are going down, which means our frequencies are going up. Now, the lowest, so if we look at the rainbow colors in this order, the Roy G. Biv, and we all know what the uses of visible light is. We use it to see and all that good stuff. So if we look at this, the red is going to have the lowest frequency and it's going to have the highest wavelength. Whereas violet is going to have the lowest wavelength and the highest frequency. And green, of course, is right in the middle. Ultraviolet light, past violet, is going to be from EM from between 400 billionths to 10 billionths. So again, we're past here, so our wavelength keeps going down and the frequency keeps going up. So UV radiation, our primary experience with that is UV radiation actually comes from the sun. The sun releases UV radiation, which our ozone layer on our Earth helps block. And so one of the concerns that happened in the 80s and 90s was that the ozone layer was depleting due to the use of certain chemicals called CFCs in the atmosphere. Since we kind of made that discovery, the people on the planet have made a concerted effort to cut down the number of CFCs so that we're going to have less damage on our ozone layer. And that has actually been successful because UV radiation is harmful. It causes things like sunburns and skin cancer. And it also affects crop life, not just people. So crops can get damaged from high amounts of UV radiation. So it was actually problematic for our food supply if we kept it up. And so we've actually had a very successful turnaround on the CFCs. And I think by the year 2050, it's expected to make a full recovery. That's just one estimation, though. So one of the uses for UV radiation is because it's so harmful to living things, it's used to disinfect certain things. You can buy cases to keep lab equipment in that bombard it with ultraviolet radiation because that'll kill off any extra bacteria or things like that. All right, we got two more. The first one being X-rays. So X-rays go from 10 billionths to around 10 trillionths. That's another. So we're getting really, 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 really small wavelengths, which means we're getting really, really, really high frequencies. Now, the higher the frequency, the higher the energy in the particles. So X-rays have particular uses. We use them for medical imaging. All right, we're all familiar with going to get an X-ray. The reason why that works is if you have tissue with bone in it, so here's a bone, maybe that bone is broken, and we have tissue like your muscle tissue around that. Well, X-rays will actually go through tissue, but they bounce off of bone. They reflect off of bone. And that allows us to see the structure of your bones while ignoring the tissue. It's also used, besides medical imaging, in security imaging. Security devices like at the airport, where they scan your bag and look for certain types of things. Because again, X-rays will penetrate a lot of substances and then only reflect back on really dense substances like bone or metal. Finally, we have gamma rays. Gamma rays are EM with wavelength less than 10 or less than 100 trillionths. So there's some gray area between the X-rays and gamma rays. So these are the most energy. We study these in astronomy to determine things about the energy composition of the universe. These are produced by atomic nucleuses. So if you remember, when we have an atom, we have a nucleus that's made up of protons and neutrons, and then electrons flying around. Gamma rays are actually emitted by the nucleus as part of something called radioactive decay. And this type of radiation is actually used in radiation therapy, usually to treat cancers. So radiation therapy uses a combination of X-rays and gamma rays to destroy cancerous tissues, tumors. And so that is our primary use of gamma rays in the medical field. Outside of that, gamma rays are mostly relegated to studying things within science because they don't have a whole lot of practical uses for which we can manufacture them. And manufacturing gamma rays unnecessarily is kind of dangerous. So unless there's a really good reason to, like life-saving medical procedures, we don't really mess around with gamma rays too much. We'll learn from them, but we don't manufacture a lot of them because it's dangerous. All right, guys, that covers everything in the electromagnetic spectrum. See you next time.